We're now going to shift gears completely and start talking about chemical equilibria. The topics of this video are going to be, first we're going to define chemical equilibria, then we're going to talk about the equilibrium constant, or K, and the difference between K and Q, which is the reaction quotient, and we're going to briefly talk about the difference between Kc and Kp, and the connection between chemical equilibria and thermodynamics. So there's many chemical reactions that happen in the world around us. They happen all the time, every day. An example might be fireworks. And oftentimes when we think of chemical reactions, we think about a beginning and an end. But in reality, this isn't really what's going on. Chemical reactions don't ever stop. They just always continue. They just may not be observably changing. So you might remember from thermodynamics, we talked about Gibbs free energy. And Gibbs free energy basically tells you the chemical potential energy. So if your reactants are at a higher potential energy than your products, then this reaction is going to be spontaneous. If your products are at a higher potential energy than your reactants, this reaction's non-spontaneous. But just because a reaction's spontaneous, it doesn't mean that this reaction only goes in the forward direction towards the products. What happens is when this reaction reaches equilibrium, you have more products than you do reactants. And similarly for the non-spontaneous reaction, the reaction doesn't just go from products to reactants. The reaction takes place both directions, but you'll end with more reactants than products once the system has reached equilibrium. Okay, so here's an example of hydrogen gas and iodine gas reacting to form HI, or hydroiodic acid. So this reaction in a closed container at 717 Kelvin will form some HI, but then you'll also have some unreacted hydrogen and some unreacted iodine that will form. And if you have just HI in a container at 717 Kelvin, you'll form some iodine gas and some hydrogen gas, and you'll have some HI that has been unreacted. So what's really going on here is that this reaction is going in both directions. The reaction is reversible. So this is an example of chemical equilibrium. In a reversible reaction, when concentration of reactants and products do not change, we say that we're at chemical equilibrium. It doesn't mean that the reaction's not still happening. We're at this dynamic equilibrium. So the rate of the forward reaction is equal to the rate of the backward reaction. So you may not have this reaction go completely to the right, or what we say go to completion. Just an important aside, be really careful about arrows. Say what you want to say. If we're talking about equilibria, you use these two arrows that are only single-headed. And resonance structures, if you're using resonance arrows, then you have this double-headed arrow. So I just wanted to mention the difference between static and dynamic equilibrium. So static equilibrium is an example like a bridge. So if you take a statics class while you're in college, you'll learn about static equilibrium. Static equilibrium, nothing is changing because all the forces adding up on this bridge equals 0. And this is really important in a bridge design because you don't want anything to collapse. You have to make sure everything's balanced. In dynamic equilibrium, the example that your book gives, the OpenStax textbook, is two-person juggling. So one person's throwing pins one direction, the other person's throwing pins the other direction. So this is dynamic equilibrium. So it doesn't mean that nothing is changing. So clearly these pins are moving back and forth, but if you take a snapshot at any given point, it looks like nothing is changing because the number of pins each juggler has is not changing at any given time. So again, this dynamic equilibrium, this is when the rate of our forward reaction and our backward reaction equal one another. That's when we reach this equilibrium state. So it doesn't mean that the reactions are not happening. They're happening. It's just that the rate of the forward and the reverse reaction are equal. We also need to introduce this idea of an equilibrium constant. So an equilibrium constant, this is the constant that basically describes when this reaction is at equilibrium, what's the ratio of our products to our reactants, essentially. And so this is the formula that we use if we have some chemical reaction, A plus B goes to C plus D, and our coefficients are lowercase a, lowercase b, lowercase c, lowercase d, then our equilibrium constant equation is going to be the concentration of C raised to its coefficient times the concentration of D raised to its coefficient lowercase d divided by the concentration of A raised to its coefficient, which is lowercase a, divided by the concentration of B raised to its coefficient, which is lowercase b. And again, this is based on the idea that rates of the forward and the reverse reaction must be equal. Quick note on standard states. So in an equilibrium constant calculation, when you see these brackets, it's important to understand that these brackets mean your concentration divided by a 1 molar reference. So this allows your equilibrium constant to be unitless. So anytime you're calculating your equilibrium constant, you have to make sure that you're in your standard state. So if you're dealing with an aqueous solution, you always want your standard state is at 1 molar, so you always want to keep your concentrations in molarity. If you're dealing with pressure, our standard state is 1 bar. So we use for pressure equilibrium constants, we keep everything in 1 bar. If you're dealing with a pure materials are essentially ignored from equilibrium calculations, and that's because your reference for a pure material is essentially that is the reference state. So it's if you're putting it in your equilibrium constant equation, you would just put a 1 in the place of a pure material. So solutes you put in moles per liter, gases are in bars, and you ignore pure solids, liquids, and solvents. Okay, another piece of information, Kc versus Kp. So if you're dealing with Kc, your equilibrium constant is in terms of concentration, so everything is in moles per liter. And this doesn't have to be solution, it could also be gases, moles of a gas per liter, which is also a solution, it's just a gaseous solution. If you have Kp, your equilibrium constant is in terms of pressure. So that's a distinguishing feature between Kc and Kp. So if you have some acid HA that dissociates to H plus A minus, if you're dealing with concentrations, you would do the molarity of H plus times A minus over HA. But if you were doing pressures, you would do the pressure of H plus times pressure of A minus over the pressure of HA. So for gases, it's easier to measure pressure than the gas concentration. So that's why we use Kp, but usually for this class we're going to be focusing on Kc, the equilibrium constant in terms of concentration.